So hello, once again, my name is Ondřej Kincl. I'm a doctoral student, and today's lecture will be about smoothed particle hydrodynamics. This is quite a robust numerical method, but we will focus specifically on inviscid fluids. So I assume that you are somehow familiar with partial differential equations, at least that you know what does it mean. Maybe that you have seen this book sometime in your life. It's a very good book if you are interested in the theory of PDEs. So I assume also that you know that partial differential equations are very useful in physics, that they are useful to describe all sorts of physical processes. Today, like almost all of physics is somehow described by partial differential equations. Probably you heard that they are very difficult to solve. So sometimes in some special simple cases, linear, you are able to find a formula which solves the partial differential equations with given boundary conditions and initial configuration. But this is very, very rare. Usually, it is impossible to find a formula which solves partial differential equation. So this is why we need numerical methods that give us at least some hint how the differential equation, how it behaves. Loosely speaking, we can divide numerical methods for PDEs into two categories: mesh-based and mesh-free methods. Maybe you know some mesh-based methods. These are very, very well known and very common. In both these approaches, we somehow need to discretize the domain, as because the computer can exist only in finitely many states. So some discretization is needed. So we divide the domain into some finite number of points. The number can be, for example, 30,000 or million. And so this is common for both these approaches. But the difference between mesh-based and mesh-free methods is that in mesh-based, you always have some additional structure, which tells you that some point will interact only with some few particles in the neighborhood. Yes, so for example, in this is a picture of a grid for a finite element method. This point in the intersection of these lines is naturally interacting with these 6 neighbors around it. Hope you can see it. Of course, if you are solving an implicit problem, then there is like a long-range interaction, but you get a sparse matrix where these neighborhoods define the sparsity pattern of your matrix. Yeah, so nonetheless, there is some underlying structure, some grid, which tells you how these points interact with each other. Examples of the mesh-based methods are finite difference method, which is very old, well studied. There are a lot of theoretical results. Somewhat generalization, somehow a generalization of finite difference method is the finite element method, which allows you to refine your mesh very nicely at some points or areas of interest. Then there is the finite volume method, which takes a slightly different approach than these two. It doesn't work with the Fick formulation, and instead it works with some fluxes between cells. But all these methods have some grid, some structure. On the other hand, mesh-free methods. In mesh-free methods, there is no grid. You still have some points which discretize your domain, but one point will interact with all other points within a certain distance. And you don't need any structure behind these points. Examples of mesh-free methods are particle in cell, or PIC method, which is actually quite old. It is nearly as old as computers themselves. And it is often used in plasma physics. Dissipative particle dynamics is another such method, which uses, in part, it is somehow a stochastical method. Yeah, so it somehow relies on probability. And the method that we will be talking about in this lecture is the Smoothed Particle Hydrodynamics, so-called SPH. Naturally, this list is far from exclusive. Yes, there are many more mesh-based methods, many more mesh-free methods. But these are maybe the most famous. As a side note, even this division into mesh-based and mesh-free method is not perfect. There are different methods which even do not fit into this separation, which is like spectrum methods and hybrid methods, which combine mesh-based and mesh-free methods together to get like the advantages of the both worlds. So let us now turn our attention to Smoothed Particle Hydrodynamics. It is a particle-based method, Lagrangian method. Lagrangian means that it somehow naturally follows the matter when it moves. And in particular, it means that in the discretization, you don't care about convective terms, which is nice. It was discovered in the late 70s by astrophysicists, Joe Monaghan and Lucy and Gingold and others. And the original motivation for the discovery of this method was the study of the solar system. In particular, they were studying how the solar system emerged from protoplanetary disk. And this protoplanetary disk, of course, contained billions of dust particles, and it was too complex to solve it by modeling every particle individually. That was impossible. However, they knew that the dynamics could be described by some partial differential equation. However, they quickly found that those standard mesh-based methods are not suited for this problem. And I think that if you have some experience with mesh-based methods, then you can guess why. Because there is no fixed geometry of the problem. Yeah, the dust is contained in some shape which changes over time. It is very complex, full of holes and spirals and a lot of topological complicated nuances in the geometry. So it's impossible, or it would be extremely difficult to do this in mesh-based methods. So they came up with their own method, which they called Smoothed Particle Hydrodynamics. And this method quickly became adapted to many different areas, firstly for fluids, and also for solids, and also for non-Newtonian fluids, fluid-solid interaction, you name it. It's a very robust method, and you will find millions of papers about it. Well, maybe not millions, but hundreds, thousands maybe, which will explain how to use this method to some particular problem in physics. So here I made a table which somehow summarizes the differences between SPH and the finite element method, because I think that some of you are more familiar with finite elements. So maybe, as you know, one great advantage of finite element method is that it is very fast, but very fast only when you have some fixed domain. Yes, because in the initial step, or before you start actually computing something in finite element method, you must find a grid, and this takes some time. Yes, so first you find some grid, and then you make some quick computation on this grid. Yes, this grid gives you some additional structure which helps you to accelerate your computation. Another very nice feature of finite elements is that you can refine some region of interest. Maybe you are studying flow around a cylinder, so you refine your mesh closely to the surface of the cylinder where all those interesting things happen. Dirichlet boundaries are very easy to handle in finite element method. So, like the most easy boundary condition, as well for other mesh-based methods. On the other hand, free surfaces are usually very difficult to handle with finite elements. There exist approaches like arbitrary Lagrangian Eulerian method and level set method, but both of these approaches have limitations, right? Arbitrary Lagrangian Eulerian method typically fails as soon as there is some change in the topology of your domain. Maybe there is some hole which will emerge. Maybe the fluid will fill up a hole, and then this method will usually fail. On the other hand, level set method is more general, more robust. Nonetheless, it has a different disadvantage. It loses precision over time. And it doesn't well conserve mass. If you have like two component fluid, then it will not conserve masses of these two fluids very well. Another maybe disadvantage of finite element method is that it is more suited to parabolic and elliptic problems. Hyperbolic problems are more difficult. Again, there are approaches, like you can use some sort of form of stabilization, and then maybe it will work. But usually this way you will add some additional dissipation, numerical dissipation into the problem. And this is usually not what you want. So now let us turn our attention to SPH. So SPH is perfect method if you have a problem with some complex boundary dynamics. You have some problem where the geometry is not fixed in some box, but evolves over time. Maybe there is a fluid with two separated components, maybe some fluid slit interaction, things like that are problems that are well suited for SPH. Another nice property of SPH is that it is conservative, meaning that you can have a scheme which will conserve momentum, energy, or whatever you need to conserve. Usually, if you find the correct discretization, the correct set of SPH operators, you can get conservation of these laws, like at the discrete level. Another, well, I already somehow mentioned this. It is very good. It is very easy in SPH to model free surfaces. This is actually somewhat like do nothing condition for SPH free surface. On the other hand, Dirichlet boundaries are quite a pain in SPH. There are many approaches how to do this, but it usually has some flaws. Like you can do this, but it's complicated. So as you can see, SPH in this sense is the complete opposite of finite element method. Another disadvantage, which I would name, is that there are not that many theoretical results concerning the error estimate in SPH. There exists some which tell you that the error is small if the particles happen to be arranged in some regular grid, but in practice this never happens. So these results are kind of useless. So it's complicated. So now let me explain briefly how SPH works. So you have some domain and you want to discretize it. So you split the domain into particles. Now by particle, I do not mean like atoms. That's maybe important to say, because if I wanted to atoms, then simulating 1 gram of material would require 10 to 23 nodes, typically. And this is unbearable at the current state of computers. So this particle should be understood as a piece of material. Yes. And to this piece of material, I can assign position, that is where its center of mass is located. The piece has some mass, A, Ma, some volume. Yeah, it occupies some volume. It's not an elementary particle. It is a piece of the fluid. And some density. Mass, volume, and density are related to each other, of course, by the relation that density is mass over volume. And then you can have whatever fields you want, which are somehow related to your simulations. But these four always appear. These are somehow directly related to this numerical method. So then what you need is something called support radius, which I here call h. And that's some positive number, which describes somehow how large radius is of the particle. Because the particle is not in a single point, it is somehow a blob which occupies some volume. So h is somehow the radius of this blob. And this must be bigger than the typical distance between particles, dr. Then the characteristic structure in SPH is the smoothing kernel, which is really just a function which has some shape like this. It is a function which is required to have radial symmetry. It is required to have compact support inside a ball of radius h. It should have at least one continuous derivative. Usually it is chosen such that it has at least k continuous derivatives, where k is 2 or 3. And it is normalized such that its integral is 1. Yes. And fifth condition, which is of practical nature, it should be easy to compute, like on a computer in a reasonable time. So you want to avoid exponentials, yes, because exponentials are somehow slower to compute. So as an example, you can have this piecewise polynomial kernel called kernel. And as you can see, it's very simple. Yeah, so it's 0 outside of the ball of radius h. And inside it is this polynomial expression. And you can check that the coefficient is chosen such that its integral in 3 dimensions over the ball is 1. So now I will try to show you how this SPH works. Can you see now this white screen?
Yes, I can.
Excuse me, what did you say?
Yes, I can.
Yes, yeah, okay, fine. So it is a method for partial differential equations. So I'm naturally interested in something like this. Yes, I have some field F, and I'm interested in the partial derivatives. This is what appears in our equations. Here specifically, I will be interested in the partial derivative expressed at some point Ra, which is the center of mass of some particle A. Yes, because I have my fields expressed in the location of these particles. So this is what I would like to somehow approximate. Yes, I have now some fields which are defined only in the particle positions, and I would need partial derivative. But as you know, derivative requires the knowledge of the whole neighborhood of some point, which I do not have. So I need to use some approximation. The approximation which SPH uses is that it replaces this derivative of function f with a convolution. Convolution with this smoothing kernel expressed with Ra. Yes, and why is this reasonable approximation? Well, as I said, this WH is compactly supported inside some region of radius h. It looks somehow like this. And it is normalized in a way such that its integral is 1. So as you can imagine, if I decrease h, I will get increasingly more spiky function. And as a matter of fact, when h goes to 0, these kernels will approach the Dirac delta in some distribution sense. Yes. So what does it mean? It means that as I let h to 0, this expression will approach an expression where I replace this WH with Dirac delta. And as you know, the convolution of anything with Dirac delta is like the identity. You get back the function origin. Yes, so this is the idea. It's basically the same as modification. And the next step is that I move this derivative from the function f to this kernel, which I can do. It's the property of convolutions. And I get this expression. And now it's good to somehow realize what is this derivative. So I have a formula for WH involving some polynomials, let's say. So I can compute actually this expression. This expression makes me happy. So what is this thing? Using the fact that WH is radially symmetric, I can in fact express it as the total derivative of VH with respect to this radial distance r. Yes, because this is the only thing that WH depends on. Times, and here will be something like d delta r over the ith component, and this is I will write this derivative as WH prime times xi over r. So this is what this function looks like. Okay. So now I can plug it in, and also I can use the definition of convolution. So this is some integral over RD, where D is the dimension of the problem. I have here the function f at point R times this thing, the H R A minus R times R A, or X I at point A minus X I over R A minus R, and the integral is taken with respect to R. Yeah, so this is just using the definition of convolution. And now I'm almost happy. Yes, because I have the derivative which I computed. I got rid of the derivative, but still I have this integral here. And in a computer, I cannot compute integral exactly. So what do I use? I use a quadrature rule. So I will replace the integral with a summation, and this is like another step of the approximation. I will replace this with the summation over all particles B. So sum over B belonging to particles. And now I will evaluate this, what is inside at point RB. So I will get FB times this derivative at RAB. And here I will have XI AB over RAB. And instead of this element, I will get the volume of the particle B. Yeah, so I hope that this was understandable. Here, with this lower index AB, I will always mean, well, RAB is the difference, RA minus RB, and RAB is the length of the vector. And so RAB is some arrow which points from particle B to particle A. Okay. So somehow I expressed the partial derivative as some linear combination of these arrows. Yeah. And one important thing in this, thanks to the fact that this kernel is compactly supported, here I can only sum over the neighborhood of the particle A. Yeah. Here I could rewrite sum over all parts with sum over all particles which are near this particle A. And this is very important. So let us return to presentation. So here, this is the recapitulation of what I did earlier. So SPH works by replacing partial derivative with a convolution. Then you move partial derivative to your kernel. Then you use the definition of convolution. Then you use a quadrature rule to somehow discretize this thing. And you express it as follows. And now you get something which is completely discrete. Yes. And uses only variables expressed at the location of particles. I hope that it is clear somehow. Is it okay? Are there some questions?
I think it's clear.
Yes, thank you. So if you have some questions, you can ask directly, like you don't need to wait for the end of the presentation. If you found something unclear or maybe wrong, then you can just start talking. So here, let us move to Euler fluid equations, because I would like to show you how to discretize these equations in SPH. So here I have written the compressible form of Euler fluid equations, where on the left-hand side you have the derivative of density and the velocity field. Here it should be understood that this dot denotes material time derivative. So actually there would be some convective term if I wanted just a partial time derivative instead. And yes, I consider here also some external force, which I, for simplicity, let it be constant, like its gravity maybe. Yeah. So of course you also need some boundary and initial conditions. And what does it describe? This set of equations. It describes inviscid fluids or ideal fluids. Now, for example, water, as you probably know, has very, very low viscosity. So in some sense, these equations can approximate the behavior of water. Although water has not zero viscosity, yes. It has some viscosity, but it's very small. However, there also exists fluids which are completely inviscid, like the superfluid component of helium. And the superfluid component somehow satisfies this set of equations. It's somehow more complicated. There is also coupling with the normal component. But it is not unreal to have a fluid with zero viscosity, at least as like physicists can measure superfluid helium has no viscosity. So our unknowns are the density and the velocity field, and to close the system, I need some constitutional equation which tells me how density will depend on, how pressure will depend on density. And if I have such a relationship, then I talk about barotropic fluid. As in principle, it could be more complicated. I could have a temperature here. Then I would need also to account temperature in the system. But let us make it simple, keep it simple as possible. Okay. So in principle, you could already replace these divergence and gradient with some discrete operators, as I illustrated earlier. Okay, you could do that, but you wouldn't get a very good scheme. And as Joe Monaghan found out, there is a very nice trick that you modify the right-hand side by expressing it in a little bit more complicated way using the Leibniz rule. So these are actual identities which hold precisely. And then, only then, you discretize these derivatives on the right-hand side. And the funny thing is that it actually makes difference. Yes, although these things are equal in the continuous setting, discretization of this thing is different than the discretization of this thing. Yeah. And the discretization of this thing is better because you get a system which looks like this. And you can show for this system that it conserves momentum. Yeah. So this trick, the purpose of this trick is to get a scheme which conserves momentum. Why it conserves momentum? You can see it from this expression here. Here, EAB denotes the normalized vector RAB. So it's RAB over the length of RAB. And you can see that this expression, if you don't think about this mass, then this expression is antisymmetric with respect to changing A and B. And exactly this fact that it is antisymmetric means, well, it's actually sort of Newton's third law, right? For every action, there is equal opposite reaction. So this gives you conservation of momentum. Another important thing is that you need to also use this trick for density to get this expression. And the reason for this is that only by doing this, you will get conservation of energy. Yes, and the reason, some deeper reason for this is that this discrete divergence operator here and this discrete gradient operator are dual to each other. Maybe you know that in continuous case, divergence and minus gradient are dual operators. And the nice thing here is that this duality is preserved in our discrete setting. So maybe this was like more technical, but you can read more about it. For example, Violo has a nice book about SPH, so we could read it to find out why this is a good thing. It also can be shown that this scheme conserves angular momentum. Yes, that's also nice. Another note that you don't need really this Monaghan's trick to derive these equations. You can derive them also directly using Lagrangian or Hamiltonian physics. Yes, so you discretize the continuous Lagrangian somehow, in some way, and then you get these formulas directly. So one additional note, or maybe few additional notes, the equation for density, the balance of mass, basically, it can be solved. Yes, you can find a closed formula expressing the density of A. So the best way how to see that this works is that you just take the time derivative of this expression, you arrive at exactly at this. Yes, so as I said earlier, you need some barotropic expression, which tells you how pressure depends on density. So the most simple possibility is to take it linear. Yes, so this is a linear expression. The pressure is the difference of the density minus some referential density times the speed of sound squared. This expression would hold precisely for an ideal fluid, but for ideal gas, but it can be also considered for other materials as a linear approximation. Some authors nonetheless prefer this expression, which contains the seventh power of density, because allegedly it somehow better fits experimental data. So there you have some speed of sound. Speed of sound in water is actually very high. It's some 1,480 kilometers per hour. And this is somewhat a problem because you have some CFL condition here, which tells you that the higher is the speed of sound, the smaller time step you need. But in practice, it is often sufficient to take the speed of sound to be 10 times some characteristic velocity, and this mimics incompressibility. This is actually called weakly compressible scheme. This is like an expression that is often used in SPH. Okay. So now we have discretized just the space, yes, and we derived that it conserves energy, but so far we haven't discretized the time, and this is actually quite tricky because even though you have conservation of energy at the level of spatial semi-discretization and you discretize time, it can happen that you introduce errors to this energy conservation, and then typically the energy will grow exponentially, so it will destroy everything. So it is important to choose a good time integration, and the one which is often used in SPH is the so-called Varolet time integration, which looks like this. Yeah, it's some stepping for velocity and positions, where I must understand that the position means the positions of all particles. Yeah, so I make this very big vector, and very big vector for velocities and big vector for accelerations. The nice thing is that acceleration depends only on positions, since I have pressure expressed by density and density expressed by positions using this closed form, which I have shown it. And without it, a Varolet time integration wouldn't work, actually. Yeah. The Varolet time integration is good because it's second order. It is time reversible, meaning that if I invert the sign of velocities, I exactly get the simulation going back in time. And one even more important property is that it preserves energy, in the meaning that there is some modified Hamiltonian, which doesn't differ much from the original Hamiltonian and which is exactly conserved by this discrete scheme. What is important is that this error does not depend on t. It depends on the size of the time step, yes, but it does not depend explicitly on time. So it doesn't have any secular increase that would grow over time. No, it's just this thing is something bounded, actually. Yeah, this formula, if you want a proof, it's quite difficult. Well, not so difficult, but quite interesting because it relies on some machinery of the algebras and the groups. It uses the Baker-Hausdorff-Campbell formula. So if you are interested, you can find it somewhere in the literature. But here, this is like beyond the scope of this presentation. However, there is a problem with this in regards to time reversibility. Yes, because plus operator is actually not associative in floating point arithmetic. So first we moved from continuous case to case discrete in space, then we discretize time, then we move another level lower and we consider finite precision. And in finite precision, floating point arithmetic, plus is not associative operator. And in particular, it means that, for example, if you take your favorite computer language and makes this computation, that you have 1, you add the half of machine epsilon, then you subtract half of the machine epsilon, then you get something like this. Yes. So it should be 1 in exact arithmetic, but you get something like this. And this means was actually that the addition is not associative, because if you could rearrange the brackets, that you would first subtract these two numbers, that would be exactly 0, and 1 plus 0 would be exactly 1. But if you put the brackets like this, you get this beast. And this is, of course, very close to 1, but there is some small error. And in the presence of nonlinear chaos, this small error actually destroys everything, which I will show you after a while. There, however, exists a trick how you can avoid this problem. And this is by converting these vectors to fixed point arithmetic. Yes, because in fixed point arithmetic, plus is associated, and you get then a bit precise time reversibility. So here I have an animation showing this. So you have in this simulation called dam break simulation, you have this column of water and you let it collapse under its own weight. Yes, so it will somehow splash to this other side of the wall. And here these are two simulations, one in floating point and one with fixed point arithmetic. And on the left-hand side, you will see that, well, we will, in the middle of the simulation, we will invert all the velocities. And in principle, it should mean that, that the simulation should return to the original state exactly. But this will be only the case in fixed point arithmetic, and in floating point arithmetic, it will fail. So I will show it. I will try to turn this on. Oh, it doesn't want to. Yeah, no. So as you can see, fixed point arithmetic manages to return exactly to the original state, whereas floating point arithmetic gets like roughly to some shape where when most of the fluid is on the left-hand side, but it's way off. So this small difference is actually important. So now I would like to conclude this presentation with some interesting consequences of this exact time reversibility. So you can show that if your simulation is guaranteed to be bounded, meaning that it doesn't happen that a particle would fly away to infinity, and this actually can be guaranteed by making walls sufficiently tight, so that there is too large potential such that no particle can ever cross this potential, then the simulation must always be cyclic. And this is because every state has a unique successor, because the simulation is deterministic. But using time reversibility, you can also show that each state has exactly one predecessor. And these things together imply that because there are only finitely many states, the simulation is always bound to be cyclic. No matter how strange initial configuration you prepare, the simulation will always return to the original state after some crazy large amount of time. This is one thing. Another consequence is that there is this disorder in this simulation, or maybe I would put it this way. You can apply directly second law of thermodynamics to your simulation, which will tell you that disorder will be self-emergent. Yes, so you cannot really avoid dissipation, even though your scheme conserves energy almost perfectly and is time reversible. You still will have some sort of dissipation, which I can show you in this benchmark. This is called Gresham vortex benchmark, where you have in the initial configuration, you have some vortex, which has everywhere zero radial component of velocity, but has non-zero angular component. And because the fluid, Eulerian fluid, has no viscosity, this structure in theory should be completely stable. Yes, this shouldn't evolve whatsoever. But in SPH, it won't be the case because there will be some friction between the particles, and the particles will somehow spread the energy over the whole domain. So I hope that I will manage to, yes, now it runs. So on the right-hand side, you can see the error. and you can see that it behaves like some noise. So it still will dissipate. And you can somehow verify this dissipation by showing that the distribution of velocities will converge to Maxwell-Boltzmann distribution. So this is the distribution of velocities in a gas. And it is the distribution which maximizes the uncertainty. So that's like a drawback that you cannot somehow avoid in this weakly compressible SPH, that you will always get some dissipation and some self-emergence of chaos. So let's conclude this presentation. I have shown you some scheme for Eulerian fluids using SPH, which conserves mass. This holds trivially because we have particles which have constant mass, and they don't, like, if they don't leak through walls, they will stay there forever. So the total mass will be forever the same. We also got conservation of momentum, as I discussed, using the Monaghan's trick. It is also possible to show angular momentum, and both of these conservation hold up to some machine epsilon. Well, actually, the error can grow over time slightly, but basically it's up to machine precision. Then we were able to get conservation of energy using symplecticity, which held up to some error of order delta t squared. And we also got time reversibility using fixed precision arithmetic, which then can hold exactly, like, in a bit precise manner. So finally, I just would like to note that there are many modifications to this method. You can have an implicit approach, which is very good, like more stable, quicker, because you can allow larger time steps. You can filter the noise, which you have seen, using some special techniques. This, however, makes the simulation irreversible. Another thing you can have is operator renormalization, which can improve the precision. But the disadvantage is that it makes the kernel non-symmetric, so it breaks all the conservation laws that we have derived. And you can, of course, add more physics like viscosity, surface tension, evaporation, just you name it. There are many articles how to add something to SPH. You can also have turbulent models in SPH. So that's probably all. I think that I made it a little bit longer, so sorry for that. And if you have some questions, then it is now time to ask.